Hi viewers, welcome back to my channel. In the last video, we saw the stiffness metrics of a simple bar element. This video is part of a set of lectures that I am doing to promote awareness of finite element theory and practice. So let's get to the crux of the topic. Today I'm going to derive the stiffness matrix for an inclined bar element, and while proving it we will see a lot of concepts that are related to this, a few from the matrix algebra, a few from coordinate transformation. We will see all those concepts in this video. So let's get started. I have a general bar element here. So this is node 1, this is node 2, and this is inclined at an angle, let's say alpha or theta to the horizontal, alpha or theta, whatever you like. This is still a bar element. It cannot take any loads transverse or perpendicular to the direction of the bar. But now I would like to know the stiffness matrix in the coordinate system xy. There is a local coordinate system x prime y prime which is directed along the axis of the bar, but let's say I'm solving a problem where there are a lot of elements like this. These are all bar elements and I'm interested to solve this in this coordinate system. So it's better if I can write the stiffness matrix of all these three elements in the global coordinate system. So that's the motivation behind this whole exercise. So I hope that is clear. And in the local coordinate system, the stiffness matrix of a bar element is pretty straightforward. So this is the displacement of this node along the axis of the bar element. This is the displacement in the along the same direction but at node 2. These are the external forces again acting at the same node along that direction, along the axis of the bar. And in the last video we saw this is how the stiffness matrix look like. But we are interested in something else. We are interested in how the stiffness matrix will look like when we have to relate the displacement seen in the global coordinate system to the forces in the global coordinate system. Remember, these are the displacements in coordinate system and these are the forces in the coordinate system. So that's what we are interested in. Let's see how we can solve for this. We can expand whatever we have written in the local coordinate system into a slightly in a better manner by considering the y prime direction displacements and y prime direction forces. This is just a mathematical exercise. Still the bar element cannot take any forces in the y direction. This is just another way of telling that your f1 prime will be 0, your f2 y prime will be 0. F1 y prime and f2 y prime denote the forces that are acting perpendicular to the bar element, which is meaningless for a bar element. So we have just put the same equation in a better manner. But now we need a methodology where we can convert a vector in the local coordinate system. So we are talking about now, say I have the vector in this coordinate system x prime y prime, but I would like to convert it to xy. How that can be done? This is the $1,000,000 question that now we are asking. This is a classic problem of coordinate transformation. You won't have to if this is the vector what we are talking about, then the vector doesn't change with respect to the coordinate system that you are working with. Only the components of the vector change. The components will be different if you are representing the vector in this coordinate system, in the xy coordinate system, and they will be slightly different when you're representing in x prime y prime coordinate system. Every coordinate system will have some unit vectors associated with that. Let's say xy coordinate system is having e1 and e2 unit vectors assigned to it. They can be thought of the I cap j cap vectors what we learned in the vector algebra. It's similar, e1 is similar to I cap and e2 is similar to j cap. And let's say e1 prime and e2 prime are the unit vectors corresponding to the x prime y prime coordinate system. Now, as I explained earlier, we want a methodology where we can have a relationship that connects these two. Say at this point, I have a force vector here in this coordinate system, let's say in my x prime y prime coordinate system, how I can convert the same force vector. So this is the force vector in x prime y prime. How I can convert the same force vector to this coordinate system? This is the question that I'm asking. Similarly, displacement is another vector. So if I generally derive a formula for any vector, I can use the same set of equations for both the force as well as for the displacement. Make sense? Now, actually, this is how coordinate transformation is written using initial notations. This is nothing. You get don't get tensed after seeing this equation. It's very simple. I'm telling the new coordinate system unit vectors can be written as a matrix times the old set of unit vectors. So this is pointing along the x direction, this is pointing along the y direction, this is pointing along the x prime direction, and this is the vector which points along the y prime direction. And this is a concise form of writing it using initial notation. Let me make it far more easy for you this way. So you know your x prime vector in in this coordinate system is cos theta I cap plus sin theta j cap, isn't it? This are called the direction cosines and all. So you are saying when you consider a unit vector along this direction, it is same as moving cos theta distance along the y I cap direction, then moving sin theta distance in the j direction. Makes sense? It's another way of telling it. Similarly, you can reach the unit vector along the y prime direction if you move minus sin theta along the negative I hat direction, I cap direction, and you move cos theta amount in the j cap direction. So it's another way of saying it. Now we need to evaluate what are q11, q12, q21, q2. We already evaluated it over here like this to get a more general idea of evaluating q1, q12, q21, q22. If you are not comfortable with coordinate notations, you can skip this, but let me just explain that. So this was our definition, how we defined the new unit vectors. So I'm telling my new unit vectors is a function of the old unit vectors like this. I'm taking the dot product with a unit vector in the old coordinate system. Then I can write it like this. This is Kronecker delta. Using the property of Kronecker delta, I can replace this j with k. So this, and from coming here to here, what I'm doing is a dot b is same as b dot a. So I'm telling any element in the coordinate transformation matrix is the dot product of the new basis vector times the old basis vector. So qik is qei prime dot ek prime. Sorry, ek. Let me just explain that with this example. So what I'm telling is your q12 is your e1 prime dot your e2, isn't it? So let's see here. What is your e1 prime? This is my e1 prime. And what is my e2? E2 is this. So my q12 is the dot product of e1 prime. This is my e1 prime to the e2 direction. What is that? It is nothing but this distance, isn't it? When you take the dot product, it is this distance. It's the projection. So this is nothing but sine theta. See, you are getting sine theta here. So I just wanted to explain how it is done using coordinate like initial notation also, so that it will be helpful down the line for you. For the time being, if you didn't understand anything about initial notation, just remember this. Like this is how we transform from one coordinate system to the other. Make sense? So now the q matrix will look like C, S, minus S, and C. Make sense? That's it. This is the matrix which helps us to transform one vector from one coordinate system to the other. It helps us to transform a vector in the old coordinate system to the new coordinate system. Make sense? We set out this whole journey asking for a relation between these two vectors and a relation between these two vectors. So the same relationship holds because this is one vector, the displacements at node 1 in this coordinate system, this is another vector, the same displacement of node 1 but expressed in this coordinate system, xy coordinate system. Similarly the force. Now with whatever we have learned, we can write these set of equations. They are helping us a lot because we derived this. The same thing holds when transforming a vector from the xy coordinate system to the x prime y prime coordinate system. There's a mistake here, this should be f1 y prime. Similarly here also the same, there is a error here, this is the one corresponds to the node. Okay, so this is the force acting at node 1 in the xy coordinate system. This is the same force acting at node 1 in the x prime y prime coordinate system. This is the displacement of node 1 in the x prime y prime coordinate system. This is again the displacements of node 1 but in the xy coordinate system. Makes sense? So this matrix is really handy. But we started this journey from this equation. Remember this? So this was written in the initial portion of the video by extending the very simple equation for a bar element in the local coordinate system. Now we can substitute for this vector and this vector. You have to be very careful here. See, this is one vector, this is one vector. This whole thing can be written like this now, isn't it? So this vector is related to this is the displacement of node 1 is related to the displacement of node 1 in the xy coordinate system. This is in the x prime y prime coordinate system. The same holds for the node 2 as well. This is the displacement of node 2 in the x prime y prime coordinate system. This is related to this matrix using to the displacements of node 2 again in the xy coordinate system. The same holds true for the forces as well. So I mean we are substituting for this now. We are substituting for this here. As we come down, see, this is a vector. This vector is related to the same vector in the xy coordinates. It is related to this matrix. Similarly, this is the force acting at node 2 in the xy coordinate system. It is related to the same vector in the x prime y prime coordinate system using this matrix. Now I can once again, now we have separate equations for this vector and this vector. Once we bring in that, let me zoom out, we can write it like this. Seems a bit lengthy, but it's very simple. I can move ahead and write my set of equations like this. Isn't it beautiful? It's a lengthy mathematical operation, but you can do it using any symbolic computation software, maybe MATLAB. Once you solve that, here is your stiffness matrix of the bar element in the global coordinate system. See, this is in the global coordinate system. This is no longer in the local coordinate system, which was aligned along the direction of the bar element. Makes sense? And once again, please pay attention. This is also symmetric, isn't it? This is also symmetric. This again comes from the Maxwell-Betty reciprocity theorem, which I have already explained in the video before this. So thanks for watching. Few key concepts were the concept of coordinate transformation, how it is derived, how it can be represented using indicial notation. Before I wind up this video, I would like to tell you one more thing. The matrix Q, which we had talked about, it was orthonormal, which means that its inverse is equivalent to its transpose. This can be proved also, again using initial notation, but I'm not going to do that. So this is how we derive the stiffness matrix for a bar element, for a general bar element which is inclined, where the C is cos theta, S is sin theta, where theta is the inclination of the bar element from the global coordinate system. Okay, makes sense. That's it for this video. Thanks for watching.